Welcome back to part 14 of our technical training series on reliability engineering and risk assessment. With our study of importance measures complete, we have officially concluded our extensive exploration of deductive modeling methodologies for the reactor vessel case study. Over the last several chapters, we utilized a top-down analytical approach, fault tree analysis, to investigate our primary system hazard, a catastrophic pressure vessel explosion. Through this deductive process, we started with that singular, undesirable top event and worked backward in time to uncover the immediate, necessary, and sufficient combinations of root causes capable of triggering it. We analyzed our calculation engine's output by looking at two critical pieces of the quantitative puzzle, our minimal cut set results and our component importance measures. This top-down mapping has provided us with a rigorous, highly detailed look at exactly what must happen to cause our specific catastrophic outcome. However, as we move forward in our risk assessment journey, we must recognize that a deductive model is inherently constrained by this singular focus. It looks only at the pathways leading to one predefined disaster. It cannot easily map out complex operational scenarios that branch into entirely different types of consequences or partial successes. Furthermore, it is critical to realize a major mathematical boundary of the analysis we have performed so far. In our fault tree model, what we actually calculated was a conditional probability, specifically, the probability that our safety systems would fail given that a runaway reaction had already started. Within that top-down structure, we did not factor in the actual likelihood or frequency of the runaway reaction itself occurring in the first place. Nor did our model account for how to calculate the distinct probabilities of entirely different end states, such as a safe shutdown, a minor venting incident, or a catastrophic explosion. This is exactly where our new chapter comes into play. To bridge these gaps, we are going to introduce inductive modeling methodologies in this session using the event tree module inside the item toolkit. This forward-looking framework will allow us to study all of these different operational cases systematically. Crucially, we will see how we can directly connect our existing deductive fault tree structures right into this inductive framework. By linking the two methods together, the software will allow us to trace a single initiating event, like our runaway reaction, forward through a sequential timeline of safeguards. By evaluating how these safety layers react in series, we will learn not only how to factor in the real-world frequency of the initial operational upset, but also how to calculate the exact probabilities for an array of completely different system consequences. This powerful combination of inductive and deductive tools will ultimately give us a fully integrated, clear picture of our total system risk. Let's jump straight over to the item toolkit user interface right now so we can open up the event tree canvas and begin building this inductive framework step by step. The first step is to create an event tree system within our project environment. To do so, simply click the event tree icon in the main toolbar, or navigate to the top menu and select Add Event Tree. This action instantly adds a new inductive system to our project workspace. If you look over at our project navigation tree window, you will see that we now host two distinct models side by side, our original deductive fault tree and our newly created event tree. By default, the software initializes the new event tree canvas with 4 standard columns. In this framework, each column we define will ultimately link to either an initiating event, a mitigating safety event, or an existing fault tree gate within the project. Now, let's look at our physical reactor incident using a forward-thinking, inductive approach. To trigger any sequence of events, we must first define an initiating event, which, in this case, is the runaway chemical reaction. This event will establish the baseline frequency or probability of the operational upset occurring in the first place. To add this initiating event into our project database, we can simply open the event list dialog box that we explored during our previous data entry sessions. Let's click the Add Global Event button, which instantly generates a new placeholder event named Event 1 in our master list. With this new row selected, click on Event Parameter to open up its Properties window so we can rename this event to Runaway Reaction. Let's update the description field to be Reactor Runaway Chemical Reaction Initiating Event. Next, we need to assign a mathematical probability to this upset. To keep our baseline calculation straightforward for this example, let's add a new failure model. We will select a fixed model, input a probability value of 0.01, and name this specific profile reaction. Now that our initiating event is established, let's trace the sequence forward using an inductive line of thinking. When the runaway reaction occurs, the very first mitigating action required by the system is to close the chemical inputs. From this node, the timeline splits into two distinct, realistic scenarios. Either the inputs are correctly stopped and the hazard is checked, or the inputs fail to shut down properly, forcing our safety systems to rely on downstream barriers. The good news is that we don't have to rebuild the failure logic for this mitigation barrier from scratch. We already have this exact shutdown action modeled inside our deductive fault tree under the gate labeled G-input. However, because this gate was created locally within the fault tree module, it is currently only visible within that specific system. To use it as a bridging link inside our new inductive framework, we need to elevate its visibility across the entire project environment. To do this, let's open up our gate list dialog box. In the filter settings, select Show All to display every node in the project database. Next, find and select G-input, and then look toward the Options panel to check the box labeled Make Selection Globally Visible. By changing this setting, the software links the underlying failure logic of that entire fault tree branch directly to our global project registry, making it instantly available for the quantitative mapping of our event tree columns. If the chemical inputs fail to shut down properly, our sequence continues forward along the failure branch to our next crucial layer of defense, the non-return valve, or NRV. Just like we did with the input shutdown gate, we need to bridge this mechanical barrier into our inductive timeline by making it globally visible. Let's open up our event list dialog box once again. In the filter dropdown, click on Show All to display every basic event currently stored in our project database. From the populated list, scroll down to Locate and select the NRV component. With the valve selected, look over to the property options and check the box labeled Make Selection Globally Visible. Now that we have elevated all of our necessary events and gates to the global project registry, let's head back over to our event tree canvas to start mapping out the actual layout of our columns. First, double-click directly on the header title of column 1. In the Properties dialog box that pops up, change the column gate/event type dropdown to Event, and then select our initiating event name, Runway Reaction, from the list. Click OK to apply the change and close the dialog box. Next, double-click on the header for column 2. For this column, we want to link our electronic isolation barrier, so change the column gate/event type to Gate, and select our global fault tree gate name, G-input. Moving down the timeline, double-click on column 3. This is where our passive backup mechanical barrier comes into play, so select the type as Event, and then choose our global basic event name, NRV. Finally, you will notice that we still have column 4 left over. Because our simplified scenario maps directly through these 3 core milestones, we don't need this extra column. We can easily clean up our canvas by right-clicking on the column 4 header and choosing Delete Column from the context menu. With our columns fully configured and cleanly mapped, let's look at the logic paths defined on our canvas. By default, the software splits every single branching node into 2 paths, which represent either the success or the failure of that column's event or gate. However, if we evaluate the operational sequence following our electronic isolation barrier, the G-input column, we realize that if G-input successfully shuts down the chemical inputs, the runaway reaction is halted. In this specific scenario, the downstream non-return valve will never be triggered or needed. Therefore, we do not need success failure paths extending from the success branch of G-input. To clean this up on the workspace, simply right-click one of the unnecessary sub-branches trailing the success line of G-input and choose Delete. Now double-click the remaining branch and choose Branch Type to Null. This action combines the branches, signaling to the calculation engine that the operational status of the next event does not matter if the inputs are successfully isolated. Now that we have tailored our sequence logic, take a look at the resulting tree structure. As you can see, our inductive model cleanly maps out 3 completely different end states, allowing us to track the system's performance all the way from a catastrophic explosion down to a minor containment incident or no operational incident at all. Now that our sequence logic and branches are fully defined, we can execute the calculation engine by clicking the Go button on the main toolbar. As you can see, the item toolkit environment is intentionally designed to maintain a highly consistent, user-friendly experience across the board. Once you become familiar with the workspace navigation, menu setups, and data structures of one module, like the fault tree workspace, transitioning into a completely different module like event trees is incredibly straightforward. With the calculation complete, let's turn our attention to the results column on the far right of the canvas. You can now see the exact calculated probability or frequency for each of our distinct operational scenarios. As we would expect in a well-engineered defense in-depth system, the no-incident scenario carries the largest probability by a wide margin, representing the normal, successful mitigation of the initial upset. Conversely, the catastrophic failure scenario, where both our active electronic isolation and our passive mechanical valve fail simultaneously, yields the lowest probability. There is also an important mathematical check you can perform here to verify the integrity of your model. If you add the individual probabilities of all three scenarios together, they equal exactly 0.01, which is the total probability we established for our initiating event. This demonstrates how the event tree perfectly partitions that initial 1% runaway reaction risk across our different system consequences. We can also evaluate our minimal cut sets and importance measures directly within the event tree module by opening up the results summary view. Inside this dialog window, you will see a dedicated navigation panel displaying our three different outcome branches. Clicking on each individual branch allows you to instantly isolate and inspect the specific mathematical results related to that exact operational scenario. If we select the branch for our catastrophic failure scenario, you will notice that the calculation engine generates exactly 11 minimal cut sets, which perfectly matches the baseline results we discovered during our deductive fault tree analysis. However, there is one critical difference to notice in the quantitative data. The order of every single cut set has now increased to 4. This shift occurs because our inductive framework dynamically adds the runaway reaction initiating event as a mandatory multiplier to each of the 11 original failure pathways. This visually demonstrates how the software mathematically combines the bottom-up frequency of the process upset with the top-down failure logic of our safeguards, providing a completely integrated total risk calculation. By utilizing this inductive approach, we have successfully moved beyond simple conditional failure rates and can now quantify the absolute risk profile for every possible branch of our reactor timeline. And with that, we have successfully completed our comprehensive analysis of the reactor vessel case study. By taking this final step, we have achieved the ultimate goal of advanced probabilistic risk assessment, bridging the gap between top-down deductive logic and bottom-up inductive modeling. We've shown how individual component failures, captured inside our 11 fault tree minimal cut sets, ripple upward to dictate the success or failure of our global safety barriers. By embedding those fault trees directly into our event tree columns inside the item toolkit, we transformed our static conditional probabilities into a dynamic, absolute risk timeline. We watched the software take our 1% runaway reaction initiating event frequency and perfectly partition it across three distinct operational end states, giving us a clear, auditable, and technically sound view of our total system risk. Over the course of this entire training series, we have covered an immense amount of ground by mastering both deductive and inductive methodologies to thoroughly analyze system safety. Rather than just focusing on abstract theory, we applied these advanced frameworks directly to a complex, real-life reactor case study to see exactly how engineering risks behave in the field. Through our top-down, deductive fault tree analysis, we systematically audited our design layers and learned how to calculate and interpret our minimal cut set results to expose hidden system vulnerabilities. We then took those results a step further by using quantitative importance measures to rank individual component risk, balancing pure structural sensitivity against real-world operational probabilities. Finally, we flipped our analytical perspective to a bottom-up, inductive framework, linking our existing fault tree gates directly into an event tree structure to map out an entire timeline of sequential safety responses. By combining these dual engineering perspectives within the software, you now possess the core methodological and practical skills required to systematically dissect, quantify, and mitigate complex engineering risks. But the best way to truly master these methodologies is through direct application. In our next and final session, we are going to pivot from a guided walkthrough to a hands-on workshop. We will provide you with a completely fresh, standalone practice example featuring a new system architecture and unique operational parameters for you to model entirely on your own. For this final exercise, we will not be giving away the solution in the video. Instead, we want you to try it on your own, build out the logic, and calculate the final system outputs. Once you have your numbers, leave a comment below the video to let us know what results you got. You can also contact us directly, and we will be happy to look over your work and let you know if your results are right or wrong. This is the ultimate way to solidify everything we have learned across this entire series. Thank you for your time and focus throughout these chapters. Fire up your item toolkit workspace, and I will see you in the final practice session.